113 is about direct and inverse variation. So, if you can imagine, direct and inverse variation are opposites of each other. So the first thing I have in your notes talks about if a store has twice as many women's shoes as men's shoes, we can express that mathematically by writing the equation L equals 2M. And that shows direct variation because direct variation will be in this form of y equals kx. Okay, this shows direct variation. Okay, k is our constant of proportionality, and really it's also slope. So what you need to know and understand, one of the things you need to know and understand is that if you were to graph a direct variation, your line will always go through the origin. Okay, it may not look just like that. The slope can definitely be greater or smaller, but it will always go through the origin. So something to your right, like this, okay, is not direct variation because it will not go through the origin. Right, because it has the y-intercept of 7. So that line is going to be, something like this, possibly. Okay, it is not going through the origin. So, all right, so I've given you a chart, one that shows direct variation and the other one shows indirect variation. So essentially, indirect variation is going to have involve division. So y equals k over x. This is indirect. All right, so for example, the weight varies directly with the volume. Okay, I've already written that one for you. W equals the constant of proportionality times the volume. Okay, so how would you write the next one? Force varies directly as current. Try to fill out this chart on your own, just kind of using the first one as your example. And I will then stop your video and then come back and see if you got them correct. So force equals K times C. Okay, it varies directly with current. Distance varies directly with time. Distance varies directly with time. Okay, so how about for the indirect variation? Pressure varies inversely with volume. I'm just going to label these as direct and indirect. And hopefully you can use the sample I put for pressure varying inversely with volume as your model for how to set up these equations. When current varies inversely with resistance, you would say C equals K over resistance. And if velocity varies inversely with is inversely proportional to time, you would say velocity is inversely proportional to time. Okay, whatever that constant is divided by time. Let's look at the problems I gave you in your notes. Thankfully, I numbered them. So number 1 says the mass of a substance varies directly as the volume. If the mass of 2 liters is 10 kilograms, what would be the volume of 35 kilograms? So the first thing you have to figure out is what is my constant? So the first thing you want to do is write your equation. It says the mass varies directly as the volume. Okay, so this is our equation we're going to use, and what you have to think about is we have 2 liters, a mass of 2 liters is 10 kilos. So that means, let's identify what the mass is. The mass is 10 kilos, and the volume is 2 liters. All right, so we want to make sure we put these in the right place. So 10 kilos equals K times 2 liters. All right, so in order to find K, because that's our goal, we've got to divide both sides by 2 liters. So that means that K kilos per liter. That's our units for our K. So now that we have K, we can figure out the volume of 35 kilograms, okay? So if we're looking for volume, we could go back here and just rearrange our formula, and I'm going to rewrite it here. We are looking for our volume, so let's divide both sides by K. So our volume equals M over K. And if our mass is 35 kilos, over 5 kilograms per liter, then V equals 7 liters. That's our volume. Okay, let's go ahead and do another example. We'll do example number 2. All right, the distance traveled by a car traveling at a constant speed is directly proportional to the time spent traveling. So this is like our D equals RT, but we're going to use K as a constant instead of R, but it's the same idea. If the car goes 75 kilometers, so let's first start with our formula. Distance equals K times time. So our distance is 75 kilometers, and our time is 5 hours. How far will it go in 7 hours? Okay, so first thing we have to do is find our constant, which is actually the rate. And we'll do it by saying 75 equals K times, 5. Divide both sides by 5. And we find that this car is traveling very slowly. I am not sure why. 15 kilometers per hour. I was thinking miles per hour. So now we can use that constant for to figure out how far it will go in 7 hours. So we just multiply 15 kilometers per hour. Definitely use your units when you're doing this so that you can make sure you're using the right units in the end. Times 7 hours. So 105 kilometers. Okay, let's do one that's an inverse relationship. Varies directly is 3. Varies indirectly is 4. So let's do 4 together. It says the pressure of a perfect gas varies indirectly with the volume. So pressure varies indirectly with volume. Okay, let's see, if pressure is 7, So I'm just going to write this out so that we have everything written out correctly, pascals. And the volume is 75 liters. Then what would be the volume if the pressure is 15? Okay, so now we're going to use these numbers here to find our K. So 7 equals K over 75. All right, just put pascals and liters there. So how do we get the K by itself? Well, we have to multiply both sides by 75 over 1. Okay, so K equals 525. So now the question is, what is the volume if the pressure is 15? All right, so now we substitute with K. So 15 equals 525 over V. Volume is what we're looking for. If we multiply both sides by V, we could have actually solved for V using our formula, but it's okay. 15V equals 525. Divide both sides by 15. And we find that V equals 35 liters. Okay, so go ahead and finish these sample problems on your page, but I also want you to complete the practice problems on page 113. That's noted in your notes. Go ahead and make sure you get that done as well.
Hello maths fans! Given the current global crisis, let's use this opportunity to do something positive and learn about exponential growth in the context of an epidemic. I'm going to run a pretend scenario where I have the disease, but because I have no symptoms, I go about my daily life, business as usual, and see where we end up. Current estimates from the World Health Organization for the virus COVID-19 give a reproductive number R0 or R0 of around 3. So what this means in practice is that if I have the disease in this pretend scenario, then I would expect to infect around 3 other people. Now there are 4 of us that have the virus, but the good news is that I'm starting to feel a lot better. So whilst I'm no longer infectious, the 3 new people that I've passed the disease on to will then go on themselves to infect another 3 people each. Now 12 people have the virus, the original 3 that I infected, plus another 9 that they went on and infected themselves. And those 9 new infections will go on and each infect another 3 people. 36 people are now ill. We've got the 9 from 5 days previous, plus 27 new infections. It's getting pretty crowded. 108 people now have the virus. The 27 people who were infected 5 days earlier have each gone on to infect another 3 people, giving 81 new cases. It's fair to say that things are now definitely getting serious. 324 people now have the virus, which is far too many for me to fit on screen. Using data from 2018, 13% of the UK population is aged 70 and above. So this means potentially 42 people from the most vulnerable age group now have the virus and face a battle to stay alive. 1 month on and we have 1,296 cases of the virus. Based on data from the Chinese Center for Disease Control and Prevention, this could potentially lead to 17 deaths. That's 17 people who have died from a virus that can be traced back to me. The good news is that by practicing social distancing and reducing exposure to others, these numbers are drastically reduced. The exact same scenario with 50% less exposure leads to only 19 infections after 30 days, where only 2 of those come from the most vulnerable groups, and therefore a very good chance that there are no deaths. The numbers don't lie. Please stay at home and stay safe.
Okay, lesson 114 is about exponential growth. In order to do this lesson, you're going to need to have your book open to page 479. So you've already watched, hopefully, this video on the coronavirus and how exponential growth applies in that situation. So that's what we're all experiencing right now, is the exponential growth of this virus. And it's funny that the book uses the example of rabbits, but rabbits, bacteria, viruses, all of these things can grow exponentially. So the very first example is the rabbits example at the bottom of the page. So it says that Jimmy had 150 rabbits. So if the number of rabbits doubled every year, he would have 300 rabbits at the end of year 1, 600 rabbits at the end of year 2, and so forth. We use R sub 0 to indicate the number of rabbits in the beginning. So the number of rabbits he started with is 150. And so we can, if you turn the page, you can see that there is a graph of his exponential growth. And of course it starts up here at 150 because that's how many rabbits he starts with. But it just grows exponentially. And that's what an exponential curve looks like. It goes up very sharply. So as an equation, we can figure out how many rabbits he has by taking what he starts with and multiplying it by y to the t. Okay, so y, we said it doubles. So his growth multiplier is that 2. Okay, and t depends on how many years. So if you turn back to page 479, you can see at the end of year 1, so at the end of year 1, it's going to equal r sub o y to the t. So r sub o is 150, that's how many rabbits he started with, times 2 to the first power, right? Because t represents the number of years. Okay, so in this case, it's after his first year, so he has 300 rabbits. R sub 2 would equal 150 times 2 squared, which is where they got 600. So what would R sub 10 be? Be 150 times 2 to the 10th power. Okay, and I would not expect you to do that in your heads. What you have to do is use a calculator. So for problems from this lesson, you're going to have to figure out how to use a calculator in order to answer these problems. And so 2 to the 10th power is 1024. So it would be 150 times 1024. Now, obviously, this is presuming that the rabbits he keeps, the rabbits that give birth, he keeps. Now, why would you want to keep 1,000 rabbits or 153,000 rabbits? Probably they're a breeder, and so they wouldn't be keeping all of that. But you can see, if he did keep all of his rabbits and bred them all, this is how many rabbits he would have at the end of time, at the end of that time. So we use this a lot in banking as well. Exponential growth is in banking. So the next example is example number, okay, so example 114.2 is about bacteria, and that would be a good one to look at. But the other one I have in your notes is on page 481. And it's about James deposited a $500 check at 7% interest compounded annually. How much money did he have after 14 years, and how much interest did he earn? Okay, so the formula you're going to have, well, we know that the amount he had at the beginning is $500. Okay, and to figure out what he had after a year, you would multiply that by 1 plus 0.07, okay, because remember, when we're finding interest, if we only multiplied it by 0.07, we would only be finding the interest. What we want to find is the interest plus 500. And so this actually should say a sub 1, because that's what I've written. So after 1 year, it would look like that, because he's had 1 year of interest. So what we have to do is our exponent is t. So t, once again, is time, okay, number of years of growth. So in the problem in the book, they said, how much money did he have after 14 years? Well, you would say A sub 14 equals 500, oh, not 50, 500 times 1 plus 0.07 to the 14th power. And that would give you his total, which is $1,000. It's in your book. It's $1,289.27. So they just wanted you to find the interest, so they subtracted off the principal, and so you were left with $789.27. We will definitely go over this a little bit more in our lesson on Wednesday. I do want you to try to do the practice problems found in this lesson on page 483. But you'll definitely need access to a calculator or to remember Desmos. That's an app. It's a scientific calculator app. And you can actually just use it as a website, or you can use it as an app. So if you don't have a scientific calculator, go there. And you're going to need to learn how to use exponents if you haven't ever done that before on your calculator at home. Lesson 115 is about linear equations. I've recreated the graphs that you have in your notes. So I ask you in your notes, what is the equation of the lines that you see? Well, we remember that y equals mx plus b, where m is slope and b is intercept. All right, so when we look at the first line, we can see that it intersects the y-axis at 1, so b is 1. And we can measure the slope either by saying y2 minus y1 over x2 minus x1, or we could actually just say, well, from this point here, we're going over 1 and we're going up 1. Since it's rise over run, we know that our slope is 1 over 1 or just 1. Okay, not slope. All right, so the equation of this line here is y equals x plus 1. So how is this line that we just found the equation for different than this thing to the right? Well, number one, our line there is not solid, it's dotted, and we have a bunch of shading below. Well, that's because that graph represents an inequality. So the equation or the inequality for that graph, it's the same slope, it's the same intercept. So the inequality just looks like y is less than x plus 1, because beneath this line would be less than, okay? If it had said y is greater than x plus 1, then the shading would be above the line. The other thing to note is the reason the line is dotted is because our equation is just simply less than. If it was y is less than or equal to, it would have a solid line. So that's how we show that it's only less than and it's not equal to. Means that the line there is not included, just what's below the line. So let's look at a couple of examples. The first one we have is y is greater than negative x plus 2. Well, what's our slope? Negative 1. And what is our y-intercept? 2. Okay, so when x is 0, y will be 2. So we draw our graph. Okay, and always make a note, it is only less than. So that means we need to have a dotted line when we do it. I'm going to go ahead and mark my graph. Hopefully you're doing that as well. All right, so our y-intercept is 2, so at 2 we have a dot. Okay, our slope is negative 1, so from this point we go over 1, down 1, over 1, down 1. And then we can draw a line. Okay, what kind of a line? A dotted line going through those points. Okay, and some people will just draw a solid line and then use their erasers to make it dotted, but if you're using a ruler, it's really helpful. You can just dot it along that line. You really should be using a ruler for this. And it says that y is greater than, I'm going to use my highlighter, y is greater than negative x plus 2, so we are going to shade above that line. Okay? How about the next one? Actually, let's do one that has 2 lines. So the very last problem has 2 lines, and what you're trying to find is where do those overlap. So let's make our graph. And let's label it. I'm going to actually redraw that one. Okay, and our equations are y is less than or equal to x plus 1, and y is greater than negative x. So let's start with y is less than or equal to x plus 1. I'm going to use blue for that equation, so I'll circle it with blue. So our y-intercept is 1, and our slope is 1. It's a positive slope, so it goes this direction. And it's a solid line because it's equal to. For our next one, I'm going to use green. Y equals negative x. That means our intercept is 0. And our slope is negative 1 over 1 down 1. So it's going to be in that direction. And this is only less than, so we want to make this one a dotted line. Use your straight edge. Okay, so for our first equation, it's y is less than so that represents this area. And for our other equation, y is greater than x, negative x. So, I mean, we could even shade up here. All of that would be shaded green. But the primary thing that you're looking for when you have two equations is this area where they come together. Okay, so oops, I overdid it. Where they overlap is what you're wanting to look at. I overdrew that line there. Okay. Go ahead and finish up the practice problems here, and we will discuss them when we're done. 116 is about rational expressions. This is all stuff that you've seen before. When we have a radical in the denominator, as we do in this case, what you've got to do is remove that radical from the denominator. So we have the square root of 3 in the denominator. Because when it's written like this, square root of 5 over 3, it's the same thing as writing as a square root of 5 over the square root of 3. So in order to get rid of that in the denominator, we have to multiply by 1 in the form of the square root of 3 over the square root of 3. And that yields us the square root of 15 over 3. The next one, and the last one we're going to do in this video, is has the square root of 2 in the denominator. So we just multiply by a square root of 2 over square root of 2, making sure that we distribute to both parts. And we get 4 times the square root of 2 plus the square root of 6 over 2. In some cases, you might have a square root that you have to simplify. Neither of these examples had that, but you guys